In this research we propose a novel aerial manipulator that is different from existing ones. AECOM. Conventional aerial manipulators either use a quadra to carry a robotic arm with very limited DOF, a grip, or even a cable, or use a very large UAV such as helicopter to carry more robotic arms with more DOF. Existing aerial manipulators are composed of a rotary wing UAV with a discrete robotic arm or gripper. The main limitation of existing aerial manipulator is the conflict between the payload capacity with the dexterity of the manipulator. In contrast, we design a very lightweight aerial manipulator that did even use a lightweight quadra to carry a 5 DOF continuum arm. For one thing, continuum arms have infinite DOFs due to the bending and twisting motion. For another, tendon-driven continuum arms have the highest payload-bearing ability among all continuum arms. By a compact design between the UAV and the tendon-driven continuum arm, our AECOM successfully solved the conflict lying in conventional aerial manipulators. In this research we further address 2 issues related to the continuum arm: kinematic modeling in the presence of payload, and tendon slacking. Existing continuum arms use PCC model based on the cable length to compute the kinematics. However, PCC model does not consider the variable payload. In this work, we propose a sensor-based modeling method to provide precise kinematic in the presence of variable payload and aggressive motions. We compare our method with conventional PCC method based on the cable length. The red line is the ground truth while the green and blue represent the method based on cable length and our method respectively. As can be seen, our modeling method can provide a much more accurate value compared to the conventional method. For cable-driven continuum arms, one common issue is the tendon slacking, which often occurs during aggressive motions. To address this issue, we propose a novel tension control method, which controls the tension of the cable to avoid cable slacking. We compare our controller with existing controllers and an attitude controller to demonstrate its performance. As can be seen, our controller can track the aggressive motion satisfactorily while the other controllers cannot. For the attitude controller, it suffers from tendon slacking after t equals 70 seconds. Finally, to further demonstrate the performance of our AECOM, we perform multiple aerial grasping experiments. The to-be grasped object, a bottle 250 gram, is placed with different attitudes to test the grasping of the manipulator. In the first grasping experiment, the bottle is tilted by 15 deg. The AECOM can easily pick up the bottle and transport it to the destination and drop it. In the second grasping experiment, the bottle is tilted by 50 deg, which increases the grasping difficulty significantly. However, the AECOM can still grasp the bottle successfully. To be noted, the motion of the AECOM is very smooth, unlike conventional aerial manipulators. Finally, the bottle is nearly parallel to the ground. Our AECOM can still successfully pick up the bottle in a continuous and smooth motion. These experiments have demonstrated that the AECOM is lightweight, but it is flexible and dexterous. Furthermore, it can perform tasks in a very smooth fashion. Unlike conventional aerial discrete robotic arms, we believe that the AECOM will have tremendous applications in aerial manipulation.